Okay, so a couple housekeeping things. Most things in the gradebook are up to date. I still have 1 or 2 kids finishing up the test from Friday. I am still chipping away at those from Friday. I'd like to think I will have those to you probably by Thursday, right? If I really last things go after school for me, I might be able to get them done tonight, but make no promises. Only other thing that isn't in the gradebook is the airbag lab that we did, the exploding stoic bag. All right, so I'll get those in as well. Other than that, you guys should be seeing everything you've turned in. Just make sure you guys take a peek at those things. All right, so what I wanted to talk about today, right, is what you guys see here. Which is all about the other 2 phases of matter that we looked at. So the last 2 chapters, we've been heavily talking about gases, right? We did gas laws, we did those gas scenarios, right? And then last chapter, we did these gas stoichiometry stuff, where we did liters into moles with all that stuff. All right, so gases, gases, gases. But remember, that's only one of our 3 phases. But we start with gases because it gets controlled by that thing called kinetic molecular theory, all right? And anytime we talk about kinetic theory, think about the particles, right? My piston chamber with the things bouncing around, the TV with the things bouncing around. Solids and liquids do the same thing. They have particles that are trying to move around. It's just to varying its extent, right? So all of the places we'll go. At the beginning of the year, I said I wanted to cover 6 things fundamentally in here. All right, we have classes of matter and we have phases of matter. Classes of matter are elements. We talk a lot about elements. All right, you guys learned that they live on the periodic table, that they're entirely made up of one type of atom. They have certain properties. They have protons, they have neutrons, they have electrons. All right, we did lots of measurable things with elements. Then we started putting them together. All right, we took a metal and a non-metal, we put it together, we made a compound. All right, it was ionic. We took 2 non-metals, we put them together, made a compound. It was covalent. All right. Then we learned how to name those compounds, right? Prefixes, no prefixes, right? And all that stuff. Symbols and charges and cross, or write what you see. All right. Mixtures is our 3rd class of matter. Still one of the things we have to cover. All right, mixtures, right, is something we haven't talked too much about yet. Phases of matter. We've got solids, we've got liquids, we've got gases. All right, so this chapter is all about solids and liquids, all right, which is going to pick those up, and we will touch on mixtures a little bit, and that's where we'll finish the year. We'll talk about mixtures and then a little bit with acids and bases with like the 3.5 weeks that we have left in school. All right, so if we're going to try to explain a lot of what's happening with solids, with liquids, with gases, we have to talk about these things called intermolecular forces. Now, intermolecular forces link to some stuff that we did earlier in the year. So the first thing I wanted to do was review with you guys how to draw some Lewis structures. Okay, and it's been a while, so I just want to go through like a series of these to make sure we can draw them. Then I'm going to teach you about what intermolecular forces are, all right, and then how we look at a Lewis structure picture and determine the intermolecular forces. All right, so Morgan, if you get the lights for me. We had a system, all right, earlier in the year we did a lot of problems like this, but it's been a while, where we would look at a compound like CH2, Br2, for instance. A picture of that compound because it's covalent, they're all nonmetals. It floats around as a molecule in this world. And if you flash back to when we talked about those, there's 2 types of ways compounds exist. In these forms, which are called crystal lattices, which we'll revisit in a big way this chapter, and these forms, right, which are the molecules. All right, so covalents live like these. They have one individual unit that could have a couple pieces that floats around that Colton could catch, like that. ionics come together like this. It's not one individual piece, it's many, many, many pieces. The covalent ones, coming back to me, thank you. The covalent ones have interactions between this molecule and its next door neighbor, the one that looks like this that lives next door. But we need to remember how to draw that molecule first before we can talk about the interactions. So there were rules, and you don't need to recopy them down. You have them from earlier on. But I'm going to sketch them so you can see. Rule 1. The furthest from fluorine goes in the middle. Except. You don't have to write it anywhere. You have this already. We're just reviewing it. All right, so we never put hydrogen in the middle. And when we look at a formula, the one that's furthest from fluorine goes in the center. So we look at this side, I've got a carbon, I've got a hydrogen, and I've got bromine. All right, so fluorine's in the top right corner, carbon to the left, bromine down here, and hydrogen over here. So never hydrogen. But if you look, bromine is 2 boxes away, carbon is 3 boxes away, carbon's going to live in the middle. Then what we did was we surrounded the center atom with the things around it. It's called the skeletal structure. And we draw the skeletal. So I'm going to have to put 2 H's, R's around. And so hopefully a little bit starting to feel familiar. Anybody remember what we did next? Before dots, there's something. The lines. You connect everything with single lines. All right, so connect with single bonds and do the electron bank. And we learned that certain elements give a certain number of electrons. Okay, so a review on how we do that. The number of dots they give are based on where they live in the periodic table. Hydrogen lives in group 1. Things in group 1 have 1 dot. All right, so I have in my formula 2 H's, the dot, so that gives 2. I've got 1 carbon. Carbon lives in group 14. It always matches the second part of the group. It gives you 4 dots. I've got 2 bromines, and bromine lives in group 17, so it's going to give you 7 dots. So our bank currently has 20 electrons in it to begin. Anybody remember how many a single line cost me? Very good. Each single line costs you 2 dots. So I drew 1, 2, 3, 4 single lines. I have 8 dots out of my bank. All right, so I've got 12 electrons to make this picture work. Then we're into the next rule. Give dots from the outside in until all are at, what number are they all trying to do? 8 with 1 exception. Who's not trying to get to 8? Very good. H is good with 2. Which means H's never get dots. The line connecting the H's, it's 2. So he doesn't need any dots. He doesn't need any dots. 2, a bond, which means it needs how many? 6. 1, 2, 3, 6. This BR needs how many? 6. All right, my bank is empty. I had 12 dots to give. I gave all 12. Now I have to look to decide if the picture is good. Is everybody at 8? We know the H is. We know the H is. The BRs are both good. Don't forget the middle guy. Is the carbon at 8? Yeah, 2, 4, 6, 8. This is a good picture. Let's go over some where there's more to it than that. All right, so let's take a look at this one. Let's say we had SiH2O. All right, so SiH2O. All right, we start simple. We get the right one in the middle. Jackson, who's the furthest from fluorine that should live in the middle? Si. All right, so silicon's in the middle. Then we surround it. Jack, where do you want to put your two H's and your O's?
Let's go left, right.
All right, so an H, and an an A. We start to get our bank. All right, Dylan Cade, walk me through the bank. How many does an SI give me? 14. 4. How about hydrogen in group 1? And there's 2 of them, so oxygen in group 16. Good. Add those all up. 12 electrons in my bank. Dylan Clark, how many did I use up making my single bonds? 6, leaving me with 6. I've got 6 dots to make this guy work. All right, Isabella, where do you want to put your 6 dots at? On the O, right? The H is good. The H is good. I'm going to put 6 dots on this O. My bank is empty. Now I look at my picture. All right, Justin, is the H good?
Yeah.
O? H?
Yeah.
SI? No, the SI's only got 2, 4, 6, and we don't have any dots left to give it. All right, so that got us into another rule. If short electrons, what did we used to do? Take 2 off one of the ones that's happy and do what with it? Push it into the middle. So we're going to take 2 off the outer one, push it into the middle. All right, then we see if that works. Justin, is the SI good now? Yes. What if it wasn't good? What would we do? Do it again. Take 2 more and push it into a triple bond to see if that would work. All right, so that's what we do if there's short electrons. Let's look at another one where what we do if we have extra electrons. Oops, take a look at this guy. How about NH2Cl? NH2Cl. All right, Antonio, start me off. Nitrogen lives here. H and Cl. Who are you going to put in the middle?
Nitrogen.
Nitrogen in the middle. Where do you want to put your H's and your Cl's?
Wherever.
Okay. Let's start with our single bond. All right, Nikki, take over from there. Help me with the electron bank. How many does a nitrogen give me in group 15? So not its charge. You're right. Its charge would be -3, but the dots just match the second number of the group. So 15 is 1, 5, so it's 5 dots. Okay, because it's in group 15. Okay, hydrogen's in group 1. What's it give you for dots? 1, and there's 2 of them, so we get 2 dots from that. And Cl's in group 17. How many dots for 17? You're right, it's 7. Right. And that does link to the charge. So remember, if I had 7 dots, how many do I need to get to 8?
1.
And when I gain an electron, just guess what charge I carry? -1. That's why group 17 is a -1 charge, because it gains an electron when we do a Cl -1 to let cross and reduce. All right, moral of the story. We have 14 electrons in the bank. All right, Morgan, take over from there. How many do we use up? 6, leaving us with 8. Aaron, 8 dots to distribute. Where do you want to put your dots? All right, so that Cl needs 6. All right, so there's 6 there. The H is good, the H is good, but I still have dots left in my bank. If I have extra dots, what do I do with them? Put them in the middle. So the double/triple, if extra, dots on center. All right, so we've got 2 dots left on the center. All right, now it's important you guys can draw these because what these look like control the intermolecular forces that we're going to talk about. All right, so what I want to do is I'm going to put a series of like 6 of these up here. All right, and I want you guys to sketch out all 6 to make sure you can do this well. All right, and then I'm going to teach you how these pictures link to the intermolecular force. So take a crack at these guys. CO2, H2O, CCl4, NH3, SiCl3F, and N2. All right, so take a song or two. All right, get yourself an answer. And we'll see how that goes.
You gotta know the kind of glow you're giving off. Baby, that's dangerous. The way your hair blows in the wind takes me to heaven and back. And the windows down, we're riding around. I bet you don't know. Thinking, girl, you make me feel like spinning me out of control with every little move you're making. Driving me wild, you know what I'm saying. Hey, shoot another smile my way, making this boy go crazy, crazy, crazy. Ain't no guessing about where you're from. When that southern draw slips off your tongue, your little town is coming out, and every time it turns me on, baby. I can get your buzz without a drink. That's what your body does with me. Every kiss is like a sip I wanna taste over and over. Girl, you make me feel like one, spinning me out of control. Every little move you're making, driving me wild if you know what I'm saying. Hey, shoot another smile my way, making this boy go crazy, crazy, crazy. Girl, you make me feel like whoa, spinning me out of control. Every little move you're making, driving me wild if you know what I'm saying. Hey, shoot another smile my way, making this boy go crazy. Crazy, I'm like, oh, you're like, oh, spinning me out of control. Every little move you're making, driving me wild, you know what I'm saying. Hey, shoot another smile my way, making this boy go crazy. You're making me go. Last night out of the blue, drifting off to the evening news. She said, honey, what would you do if you'd have never met me? I just laughed, said, I don't know. I could take a couple guesses though. And then tried to dig real deep. Said, darling, honestly, I do a little more offshore fishing. Take a few strokes off my golf game. If I'd never known your name, you'd be driving that old green Nova. I probably never would have heard of yoga. Be a better football fan. But if I was a single man, lonely out there on the line, I'd be looking for a woman like you. Well, I could tell that got her attention. So I said, oh yeah, I forgot to mention I wouldn't trade a single day for 100 years the other way. She just smiled on her eyes. And all of my girls, seriously, if I hadn't been so lucky, I'd been shooting full in the bachelor pad. Playing bass on a cover band. He's stocking up Bud Light. Poker every Tuesday night. I have a dirt back in the shed. I want one more pillow on the bed. I keep the cash in a coffee can. But if I was a single man, lonely out there on the line, I'd be looking for a woman like you. She knows what a mess I'd be if I didn't have her here to be sure. I whispered in her ear, you know I get sick deep sea fishing. You make the best fried chicken. I got a hopeless golf game. I love the sound of your name. I miss that old green Nova. I love watching you do your. I take a gold pen on my hand over being a single man. 'Cause honestly, I don't know what
Yeah, that's my one. Okay, so let's walk through these ones, and then I'll do N2 together, just because people either haven't gotten there yet, or we just were. So CO2, job well done, right? C goes in the middle because it's the furthest from the fluorine. 1 O on each side. Doesn't matter where they are. You could have left and right. You could have top and bottom. Where these are fine as well. We get our bank. Carbon's in group 14. It gives me 4. Oxygen's in group 16. It gives me 6. So we had 16 in the bank to start. We had 1 line each to start. That cost us 4. And then we had 12 dots. All right. So Antonio said 2, 4, 6. Or who was this? I'm sorry. Jimmy said 2, 4, 6, 8, 12. It was, but then he realized the carbon in the middle wasn't happy. So he took 2 off the outside, pushed it into a double bond. Carbon was still not happy. So then he did the same thing up on that. Then we went to H2O. Who did H2O for me? Dylan. Dylan said, I got to put O in the middle because H never goes there. H on each side, single lines to start. He says the H is in group 1. It gives me 1, but there's 2 of them. So 2. Oxygen, group 16, gives me 6 to start with. Used up 4 of them. With my single bonds, I had 4 dots left. H's never get dots, so the extras all go onto the oxygen in the middle. All right, who put up the CCl4 for me? Did it just magically appear? Who put up CCl4? Justin, that was you, wasn't it? Okay, focus. Okay, so Justin put C in the middle. All right, C on the outside. You bank cells in group 17. It's 7, but there's 4 of them. So it's 28 plus the 4. That was 32. Take away 2, 4, 6, 8. You're down to 24. So he filled up the CLs, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Bank was empty. Everybody was good. You jump over to the NHP who put this one up. ID Antonio. He said put N in the middle because H never goes there. 3 bonds to the H's. There were 8 in the bank, 5 from the N. 3 more there. Take away 6 for the bonds. 2 dots left, none on the outside. So we are good to put that in the middle. Last but not least, all right, we have SiCl3F. Who put that one up for me? All right, Dylan. Dylan put that one up. Si in the middle. All right, puts 3 CLs, and you could have had the F on top, right, bottom, or left. Doesn't matter. All right, all single bonds there. All right, sorry, I erased some dots when I was pushing electrons. All right, but we fill up our outer ones. This guy is good. I'm just erasing some space for you. All right, N2. If we only have 2 elements listed, some people are like, how do you decide who goes in the middle? And you don't. You just side by side. So you start with them right next to each other with 1 bond. Then go get your bank. An N in group 15 gives me 5. So I had 10 electrons in the bank. Use 2, bless you, making the single bond. 8 dots left. My biggest tip to tell you in these ones. Don't be happy before you go to the other. Don't do 4 and 4 because then neither are happy. So get one of them to be 8, then advance on to the next. That means this end needs how many? 6. So I used up 6 of my 8 there. I still have 2 left to put them on there. Is the N on the right happy? No. And now because one of them is filled, you know which one to take the electrons off of to do the multiple bonds. If neither was happy, you don't know how to pull the electron. So we're going to take 2, push them into the middle. Is the N on the right happy? Still not. What do? Do it again. Take 2 more, push them into the middle. Is that N happy? Yes. All right. So now, drawing the pictures, we can decide what types of intermolecular forces that they have. Right? And they come in 3 styles. Right? The first is the strongest. All right? It's known as a hydrogen bond. The second, right, is called a dipole-dipole interaction. And the third is called a London dispersion force. All right? A London force, they call them van der Waals sometimes. All right? Any of those will be good. All right, Morgan, get the lights for us. All right, so if we take a look here, I want to highlight the difference between an intermolecular force and an intramolecular force. What you guys just did by drawing these pictures, you were drawing intra, I-N-T-R-A, molecular forces. You were drawing covalent bonds. This is what a picture of a covalent bond looks like. Ionic bonds and metallics, they make crystals. So if I wanted to draw a metallic bond or an ionic bond, I'm holding an ionic because I've got a metal and a non-metal. If it was metallic, they'd all be the same color sphere, right? Because they'd be all positives. Those are bonds. Right? Now, here's the catch. Ionic bonds have ionic intermolecular forces, right? The bond and the intermolecular force are the same thing. A covalent bond, its intermolecular forces have different names than the bond itself. So we have a covalent bond, but these 3 things are the names of their intermolecular forces. A metallic bond has metallic intermolecular forces. So for metallics and ionics, they have the same name for the 2 forces. But for covalent, the covalent bond and the molecule has a different name than the hydrogen bond, or than the bond, the intermolecular force that holds. All right, so I want to walk you guys through each of these. All right, but let's go ahead and take a quick breather. Let's take 5, come back, we'll hit it fresh, and we can learn about our IS. Hey, Siri, set a timer for 5 minutes, please.
Your timer is set for 5 minutes.
Yeah, what's up? I do. So my sister-in-law and my brother live in Australia. She's a naturalized Aussie. So I make Siri's voice sound that way just to remind me to stay in touch. You can change yours. You can do all sorts of
I
accents.
don't have cereal on my
You can do British. You can do.
My favorite one is the Scottish series because it sounds angry.
That would be funny.
So how am I supposed to go to a giant piece of like I don't know. What am I supposed to bring a name on? You know what I mean? Like if I was decorating some house, what am
Hey, just don't forget, you guys are still getting recorded.
I still what? So you could actually be recorded?
Recording the lesson.
I don't want
Okay, so what I want to do is talk to you guys about when I look at a picture, how do I know if it has a hydrogen bond? How do I know if it has dipole-dipole? Right? This is tricky because it incorporates a couple different ideas. We got to be able to draw the picture, and then we have to be able to interpret the picture as well, which I'm going to teach you how. All right, first things first. Hydrogen bonds tend to be the easiest to spot. A hydrogen bond meets the following criteria. It obviously must possess what element? Hydrogen. And the second thing it has to have a hydrogen connected to an element that has dots on an N, an O, or an F. All right, so it's got to have H connected to an N, an O, or an F with dots. So we work our way through. All right, I'll go ahead and do that in red. All right, Morgan, get the light for us. All right, take a look at this first one. CO2. Can it have hydrogen bonding? No. What's it missing? No hydrogen. All right, so H bond. No go. All right, how about the water? Yes, it's got hydrogen, and what's it connected to? An N, an O, or an F that has dots. This is a winner. He has H bond. How about the CCl4? No H bonding. Doesn't have hydrogen. How about the NH3? Yes, it's got the hydrogen, and what's it connected to? An N with dots on it, right? N, O, and F are our three winners. This guy has an H bond. How about SiCl3F? No go. Doesn't have the hydrogen. How about N2? No. All right. So if it has a hydrogen bond, what do we know? Well, one thing we know is it's got a strong intermolecular force of attraction. H bonds are strong, right? And what it means is the water you see here will be attracted to the next door neighbor fairly well. DNA does this incredibly well. You guys learned from Mrs. Sherry last year that you have certain base pairs that go together. I showed you the thymine adenine one, a T with an A. What's the other pair you guys had to learn? Close, guanine and a cytosine, which is a GC pairing, right? If you guys were working with RNA, all right, it's not a thymine, it's a with a U for uracil. All right, so little differences between the DNA and the RNA. But the moral of the story is, why do they get paired that way? Why does A go with T? Why does G go with C? It has to do with hydrogen bonding. These compounds, or these complex structures that you see up here, these amino acid base pairs, all right, and what happens is you get H's on those NH2 groups that are attracted to the unshared pair of dots on the oxygen or the nitrogen in those benzene rings. And you guys might not know all that terminology, and that's fine. Just understand it's a hydrogen bond. You've got C's with G's, and a GC pairing is actually stronger than an AT pairing, right? Because it's got 3 hydrogen bonds that holds it together. Because it's got an additional hydrogen bond and it's more attractive, it can pull it a little bit closer, which is why your double helix isn't just like a tunnel, right? Like if you hold up the double helix, is it like looking through like a paper towel roll? No, right? What's it look like? It's a spiral, and the spiral has narrow sections and wide sections. They call it the major groove and the minor groove. That's all because of the chemical structure and the base pairings when they come together. Moral of the story is they all possess hydrogen bonding. They have hydrogen, and they're connected to a nitrogen, an oxygen, or a fluorine that has dots on it. It's a strong connection. Category 2, I left this blank so we could draw what a dipole-dipole interaction looks like. It looks a lot like a hydrogen bond, but what happens is the positive end of one molecule interacts with the negative end of another. It says the molecule must be polar. Anybody remember how we decide if something was polar or not? So that's one way. They're attracted to water. We're going to get a little more specific, and that's what I want you guys to fill in here on this slide. So there are rules. And now that we're good at drawing the pictures, we just have to interpret the picture. All right. So to be polar, when I'm looking at a picture, yes, you should. This should go into that blank space I left on the slide. All right. To be polar, all right, rule number one is an automatic. Dots on center atom. If you see a pair of dots, an unshared pair of electrons on the center atom, the substance is automatically polar. Don't look at anything else. You can say it's polar no matter what. If there's not dots, you have no dots on center, what we do is we see if it's pulled on even or uneven. Even tool, which is all the same elements, equals non-polar. If there's no dots on the middle, right, and it's an uneven tool, there are different elements surrounding the center atom. It is polar. Why is this important? It's important because if you're polar, you possess something called a dipole moment. So I'm going to sketch out for you what a dipole moment is, and then you're going to see how we get what we call a dipole-dipole interaction. All right, so I'm going to pick a substance that is polar. All right, for instance, right, the following substance would fit that criteria. We're going to say I don't want it to have a hydrogen bond. So let's say we've got SCl2. And if I sketch this guy out, S lives in the middle. We have Cl's on the outside. My bank tells me I have 6, I have 14, I have 20, take away 4, I have 16. 2, 4, 6, 8, 10, 12, 4 left. They go on the middle. All right. Start simple. Does that have hydrogen bonding? No, no hydrogen. All right. Now we have to decide if it has a dipole moment, which means we need to know if it's polar or not. So we look. Check number 1. Does it have dots in the center atom?
Yes.
Yes. So this is absolutely polar. If you are polar, you have what we call a dipole moment. Here is how a dipole moment works. You've got Cl and you've got S. They attract electrons differently. Remember, we learned the hottest kid at the dance was fluorine, the most attractive element. The closer you are to fluorine, the better you are at attracting electrons. So chlorine lives right next door to fluorine, so it's very attractive for electrons. So the electrons that are in this bond lean toward the chlorine. So because it's got these dots on the outside and these electrons lean toward the chlorine, this chlorine is kind of negative. Right? It's not a full -1 like a charge, like Cl -1. Right? It's got what we call a partial negative, and that lowercase Greek delta is the symbol for partial. Right? So that just means partial negative. That means that the sulfur, because the electrons are moving away from it, feels kind of positive, which means the sulfur's got a partial positive charge.
How do you know which fluorine you're going?
it goes to both. There'd be another partial negative over here. Just remember, the electrons favor the one that's closest to fluorine. That's always going to be your partial, negative, the one that's closest to fluorine. All right, now here's what's going on. An intermolecular force isn't this. What you've just seen is what we call a dipole moment. All right, so that is a dipole moment. When you have a little negative in one place and a little positive in another, it's a dipole moment. An intermolecular force is this red guy interacting with his next door neighbor, and it could be the same molecule or a different one. So I'm just going to bring in another SCl2, except this time I'm going to draw it vertical. I'm going to draw the Cl up top, the S here, and the Cl down here. Same substance, so it's the same picture. Where's my partial negative at? By the Cl, right? But nothing has changed. So I've got a partial negative here. And where's my partial positive? Right here. So what happens is when this blue particle gets close to the red, a partial positive sees a partial negative, and what do we know that opposites do? They attract each other. So you get an attraction force between that opposite charge, right? The partial positive attracts the partial negative, right? And because it's the dipole of one being attracted to the dipole of the other, it is known as a dipole-dipole interaction. So it's opposite charge attraction. It's just, think of it like fractions, right? It's not a -2 being attracted to a +2, like when we cross and reduce. It's like a -1/3 being attracted to a +1/3. They just call it a dipole moment when it's a little guy. If you're polar, you have dipole-dipole interactions. Right? If you're non-polar, you don't. Right? So now that you know what one is, now what we got to do is look to decide, do these guys have a dipole moment? Right? So we have to decide if they're polar or not. All right, so you look at this guy. Does he have dots on the center? No. Is he surrounded by different elements or the same element? Same element, which means it's an even pool. If you're even pooled, what are you? You're non-polar. Do you have a dipole moment? Nope. You do not have dipole-dipole interaction. Look at this guy. Does the middle guy have dots? Yes. Is it polar then?
Yeah.
Yes. Does it have a dipole-dipole? Yes. Right? And you'll learn later a hydrogen bond is just a really strong dipole-dipole interaction. So I'm kind of being redundant listing them both. I just want you to understand how to identify. All right, look down here. Dots on the center? No. Even or uneven pool? Even because they're all chlorine. All right, so is it polar or non? Non-polar. Does it have a dipole? Nope. So this guy doesn't have H bonding or a dipole moment. NH3, what are you guys thinking? Polar. Why? Dots on the center. All right. Will it have a dipole-dipole? Yes, because you're polar, he has dipole-dipole. All right. How about SiCl3F? Dots on the center? Even pool or uneven pool? Uneven, because the fluorine is different. All right. So is it polar? Yes. And if you're polar, do you have a dipole? I bet you do. The NH3? Yeah, but we didn't even have to go that far because we had dots on the center. So as soon as I see the dots in the center, I know it's polar automatically. Yeah, so I only do the uneven even if there's no dots on the middle. Because you have dots on the middle, you're automatically polar, which means you have a dipole. All right, last but not least, the N2. All right, dots on the middle? Yeah, there is no middle, right? So we got to look. Is this guy even or uneven? Even. It's just an N connected to an N. It has to be even. Which means, does it have dipole-dipole? Nope. Because it's non-polar.
So if H bond is just the dipole, does that mean everything bond is polar?
Absolutely. Absolutely. All right, so you guys just learned your second intermolecular force. It's called a dipole-dipole interaction. You now know how to identify one when you look at a molecule. If it's polar, it's got a dipole-dipole. If it's non-polar, it does not. All right, so the million-dollar question is then, well, if you're non-polar, what do you have, right? You don't have a hydrogen bond. You don't have a dipole-dipole. What can you have? You get London dispersion, because everything gets London dispersion. All right, so all substances get what we call London dispersion forces. Now, do they all get them the same? They do not. Okay, I want you guys to circle or star or something the phrase right here on the bottom. London forces increase with the size of the molecule. The bigger the London dispersion force, all right, the bigger the molecule, right? And the reason why is it has what we call a more polarizable electron cloud, all right? Now, this is getting a little bit on the heavy end. You guys just need to know it's as simple as everything has London dispersion, and the bigger the molecule is, the more of it they have. That's your responsibility. I want to show you what a London dispersion is, though. Morgan, get the lights for us. All right, so if you look at this guy, you know how I just taught you guys about the dipole-dipole interaction and what is attracting each other in this dipole-dipole interaction? The partial positive and the partial negative. Is the partial positive always there? Yeah, because the uneven share of the electrons means the chlorine is always negative and the sulfur is always positive. So it's consistent. It doesn't go away. This partial negative is always there. It's consistent. It doesn't go away. And because they're always there, we establish a good interaction. A London dispersion is similar. The difference is they don't stay permanent. They come and they go. They come and they go. Here's how it happens. All right, say I'm looking at this end-to-end bond. All right, these electrons, all right, are getting shared in between the two ends. All right, they would move toward the one that's more electronegative, the one closer to fluorine, but what do you see about N and N? They're the same element, right? So they can't attract differently. But don't forget, electrons are in constant motion. So imagine I let you go anywhere you wanted in this room. Would you guys always be perfectly spread out from each other if I let you randomly walk around? No. Would you be grouped near each other sometimes? Yes, but would you stay there if you kept being allowed to walk around? No, right? So we might get small groupings of electrons that make us a little bit negative, but then they can just walk the other way and it goes away. So you get what we call an instantaneous dipole, a temporary dipole, but then it goes away. They call it a fleeting moment. All right, so the moral of that story is you get that opposite charge attraction for a minute, but then it's gone. You get it for a minute and then it's gone. All right, so everything has the ability to do this because atoms are moving around at all times and electrons are moving around at all times. And that's why you're seeing about polarization, the bending of the cloud. All right, so why am I talking to you about all this? Why do we have to do all this? It's because the stronger the interactions are, the closer together particles tend to be. And remember, the more tightly you're packed, what phase do you tend to be? A solid. So this is how we tend to be able to decide if substances are going to be solids, liquids, or gases. Solids have really strong attraction. Liquids, not as much. All right, gases, even less. So I'm going to remind you about the types of attractions. All right, and now we have all of these, right? The strongest that we'll talk about tend to be metallic bonds. There is something above it, but for us, we're just going to keep it at metallic. Ionics are next. All right, then we're into our covalents in terms of strength of connections. And then you get your intermolecular forces between covalents. Hydrogen bonds, dipole-dipole, London dispersion. The higher up on the list you go, the more likely you are to be a solid. And that is worth writing down. On the right side over here, right, in this little segment, go ahead and say the higher up on the list that you are, the more likely you are to be a solid. Right? The higher up on the list that you are, the more likely you are to be a solid. Right? So if I asked you, right, copper is a metal bond, what phase would you expect it to be in? Solid, because it's at the top of the list. If I said an ionic substance, and remind me again, where are the ionics at on the table? How do we get something ionic? Opposite sides of what? The staircase, right? Remember the red line that divides the periodic table? One from the left, one from the right's ionic. So if I said, hey, we've got MgCl2, it's ionic. What phase most likely is MgCl2? Still high on the list, still a solid. You don't really start to see liquids until you start seeing covalently bonded substances for the most part. All right, so ionics and metallics tend to be solids. Covalents often are gases, sometimes are liquids if they have strong intermolecular forces, which ties things up in a neat bow for us. All right, if we take a look, we know all of these have London dispersion, right? All right, so Morgan, hit the lights. Okay. If I work my way through this list, what force does he have? Only London dispersion, right? The non-polar just confirmed we don't have a dipole-dipole. He only has London dispersion. They're weak, right? What phase is carbon dioxide usually? The gas, because it doesn't have strong forces to hold it together. Water has hydrogen bonding, dipole-dipole, and London dispersion. It's got a lot of force of attraction. What phase does water usually live in? A liquid. It's covalent, so it doesn't tend to be a solid, but it's got a lot of forces for a covalent, so it tends to favor a liquid. All right, we look here. All I have for CCl4 is a London dispersion. Most likely, what phase would you guess it to be? Gas. You would learn that maybe if there's enough of these, it could be a liquid if it's a really big molecule, but I would expect you to guess that that would be a gas. Up here, how about NH3? What might you expect it to be? A liquid, and ammonia is a liquid because it's got hydrogen bonding, dipole-dipole, and London dispersion. Lots of attraction means it is probably a liquid. How about this guy here? Yeah, I don't know. It's the only one we have that just had a dipole-dipole, a London dispersion. So it might be a liquid, it might be a gas. It depends. All right, how about N2? Only London dispersion. What would you expect? A gas, and sure enough, nitrogen floats around us as a gas all the time. All right, so this is how we link the molecules to what we see in the real world. So that's a good place to put a pin in it, and I'll get to Zach's question. All right, let me take a look. I was going to give you guys some book work. All right, just some practice problems. I just want to see if we covered the IF stuff, and if you can just look up the other stuff. So 366, 1 through 5. All right, so for you guys, let's hold tight on that. 388, 1 through 3. Okay, all right, so we'll tackle that assignment when we get through properties of liquids, which will be what we cover, part of what we'll do on Thursday. Zach. So we artificially make it be a liquid by cooling it, just like anything, right? Like we cooled it off to the point that even more forces could form and let it liquefy. So the temperature can manipulate a lot of that as well.
So that's why it's still like
Exactly. That's why it's super cold. All right, at home, folk. All right, that's all for today. All right, good work. And you guys have a nice day.